Hi there, I'm going to take a short departure from the usual, and instead of vintage computers this week, we're going to be doing vintage communication gear. So what I did over the Christmas break was I earned my ham radio, my amateur radio operator license general class. And at the same time, I also managed to get my hands on some old ham radios. These two radios here, these are Drake's. They were made maybe early to mid 70s. So this one here is a Drake R-4B. This is a receiver. This one over here is a Drake T4XC, slightly newer, and this is the transmitter. So receiver and transmitter, you put the two of them together, you have what is called the Drake Twins. And they were popular to use back in that era. So these are tube radios with a few semiconductors inside of them. But mostly tube designs. They operate on the high frequency band, so approximately from the 10 meter band down to the 160 meter band, and that corresponds roughly to, I would say, around 2 megahertz to 30 megahertz or so, about that range. I actually have quite a long antenna, like a 60-foot antenna sticking out the window of the office. And then I can transmit and I can receive. I typically operate in the 40 meter band, which is the 7 megahertz band. Anyway, you don't necessarily have to understand all of that radio stuff in order to appreciate this video, because what I'm going to build is something called a Panadapter. And what the Panadapter is going to do is to let me couple this radio to my modern computer via a software-defined radio dongle, so an SDR dongle. And I will be able to visualize what is happening on the band. So let's get to that. Let's start talking about what a Panadapter is. Okay, so what is a Panadapter? To understand that, I think we need to start by understanding a little bit about how our radio works. So this ham radio, as well as most ham radios, is a super het receiver. It's actually a double super het, and what that means is it uses mixing to convert frequencies and then amplifies the converted frequencies. So your radio frequency will come in through the antenna. It goes through kind of a broadband RF amplifier, and then it gets in here into this mixer. And this mixer will take a desired frequency down here from the tuning dial. Tuning dial is down here, and a crystal selector. It will take the desired frequency, it will mix that with the incoming frequency, and it will output a frequency that is centered on 5645 kilohertz. And once you've done that, you can do your filtering and amplification on 5645. Then you take that 5645, you run it through another mixer. This one mixes it with a 5595 to get a 50 kilohertz frequency. So now your incoming frequency, which might have been 7 point some odd megahertz, is now centered around 50 kilohertz. And then you can run that through more filters, amplifiers, etc., noise blankers, whatever, amplify it, meter it, and then send it out all the way down here to a detector and turn it into audio. So the important thing to understand is you have two of these mixing stages. This first one takes your desired radio frequency and centers it on 5645. Now, if we were to go in here to this first mixer point, and we were to pick off right there, what we would have is a broadband view of the band you're on. So the frequency you want would be centered at 5645, but to either side of that frequency would be other frequencies in the band. So let's say we take that out and we run it through a spectrum analyzer. There'll be a big peak in the middle where the frequency we're looking for is, but then to either side of it, there may be other frequencies, so other peaks. And then over here, but you'll be able to see the full band. That is your Panadapter. It's kind of like a spectrum analyzer, but whereas a spectrum analyzer is usually of a relatively limited spectrum, this Panadapter attempts to sort of visualize up to and including the entire band. So you could have easily, in the case of our 40 meter band, maybe you want 300 megahertz bandwidth. You know, you want this display to go from 7 in the middle out to 150 on either side, perhaps, you know, and then you move it back and forth. So this can be a really useful visualization tool, because no matter where you are, you can see that, oh, there is another signal over here and one there and a really strong guy over here. You know, maybe I want to tune down that way and see what's there. Or maybe I want to tune up this way and see what's going on there. So that is kind of the whole Panadapter concept, at least as well as I can explain it. Now the next question is, why can't you just take your spectrum analyzer and just hook it up right there to this 5645 kilohertz output? Well, the problem is this old tube receiver is a high impedance receiver. It is driving signals that it expects to go into, you know, loads that are on the order of hundreds of kilo ohms or even mega ohms. If you take an RTL SDR or any other kind of piece of test equipment or receiver and you hook it up to this high impedance signal, it will probably suck all of the signal right out of there and kill any signal to the rest of the receiver, rendering the whole effort kind of futile. And it may even kill the signal to the point where it doesn't even have anything to display itself. So what you really want to do is you want to insert into here a buffer. And what this buffer will do is it will take the high impedance over here, and then without putting much of any load on it, it will amplify it. It doesn't even have to amplify it. It could just be unity gain. It could do 1-to-1. But it will take that high impedance and it will output a low impedance signal to our spectrum analyzer or our RTL SDR dongle or whatever we want to use. So that's what I started out doing. I kind of read about these Panadapters. I decided I'd like to add one of these to my ham radio, and I started looking at what can I put here at this first mixer stage in order to do this buffering. And I found that DX Engineering, they actually sold a board that was marketed to do that. It's this little bluish, purplish one down here. It's got some kind of amplifier chip, capacitors, resistors. There's actually some really teeny tiny, like a UFL connectors here for some tiny coax to go into it. Runs up to like 30 volts. I thought this was going to be the ideal thing. I had seen where someone else had done a project and used this and built a Panadapter out of it. But I tried it and it did not work very well at all. I hooked it up to here and it just absolutely killed my signal. And then looking online, the issue with this board is this is still a low impedance board. It expects to be hooked up to modern transistor radios, not old tube radios that are high impedance. So it sucked away most of the signal. There was a little bit left, but it was mostly gone. Now, one of the other guys, if you read his article, I think what he did is he hooked this board up over here in the noise blanker, like right here. I don't know about that approach. I mean, certainly you've kind of taken it out of the signal pipeline, so you're not going to kill the signal, but I don't know if you're just disrupting the ability of the noise blanker to work if you hook it there. I'm not sure. Maybe this is a lower impedance signal. I haven't really explored it. The other problem is you would be limited to the 50 kilohertz bandwidth that you've got there, where I really wanted to be out here on the first mixer where you can see the entire band. So I wanted to go with this solution where I'm buffering out here with a high impedance buffer after that first mixer. So what I did, first I went onto the Drake forums and asked for some advice, and some of the guys there, they pointed out, want the high impedance amplifier, use a FET follower. I looked for FET followers and I found this circuit here. I've kind of changed it a little bit, but this circuit here came from the Drake transmitter, and this was a buffer that is inside of the Drake transmitter, the T4XC, as part of its carrier oscillator. And what it is, it's based on a 2N5950 transistor. As I said, these Drakes, they have a few semiconductors in them. This is one of the semiconductors. And it is a high impedance amplifier. So you can see it's got a 10 picofarad cap. And it's got these big high value resistors, 1 meg to ground, 6.8 megs up to its positive voltage. It's a FET follower, so this is the gate coming in, this is the drain, this is the source out here. And it's going to take and amplify this signal here out this way. So this is, this is right out of what Drake did back in the 70s, and if it was good for them, even though they used it in a different part of the transmitter, should be good for me. And the bonus to me is I already had all of these parts. So in particular, I had some of these 2N5950, I think they're JFET RF amplifier transistors. I had some of those because I got them as spares for the Drake transmitter. The rest of this is pretty simple. Here, this is actually 0.001 UF. Better mark that one down. So your input here is going to come in from V2 pin 5. V2 pin 5 is right here. And it corresponds to right there out of that first mixer. So it is actually the plate of that mixer vacuum tube. Get that, take it and you run it into the amplifier, then we go out, and this goes out to SDR radio. Now we need 12 volts. The Drake did not have a 12 volt supply in it, so what I did is I added a little bit more here. I put a diode and a capacitor, and this is to the 12.6 volt AC heater. So these tube gear, typically there's a heater that's used to heat the filaments in the tubes. There were some other places I could have pulled my juice from, but I pulled it from that 12.6 volt AC heater. I'm also using this juice for a few external things to power my digital readout and stuff like that. So anyway, it's just a simple half-wave rectifier. You dump it into a capacitor. I think this capacitor was 1000 UF. That gives you your 12 volt that you can do to run the rest of this stuff. Now you'll notice there's no regulator here. So this is, I put plus 12, but it's really like plus 14 to plus 18, and it kind of oscillates a little bit. I mean, it's not a huge oscillation, but a little bit of oscillation there. Next time I come around and do this, I may put in a regulator, either a Zener shunt regulator or something else here, because this oscillation be about 60 hertz. You know, it could find its way out this path into the radio. It could find its way down this path into the Panadapter. Probably be a good idea to get rid of any potential oscillation, even if it is 60 hertz. So revision 2, I might do something about that. But for now, it's just simply the circuit out of the Drake manual, together with 12 volts, in and out. Piece of cake. And then here is the underside of the Drake R-4B radio, so I can describe the modifications I made. If you haven't looked at one of these before, it's kind of interesting construction. This chassis is all copper plated. That's why it's all coppery looking. One of the things to look out for if you buy one of these on eBay is that the copper isn't all rusted up, particularly from the top. The other thing is the construction technique. You know, if you haven't dealt with vintage gear, this was kind of what it's like. There's wires going every which way inside of it. There's circuit boards that do not have connectors to them. You've just got a wire will just come out of something and just be soldered directly in the circuit board. To pull a circuit board, you got to desolder the whole thing. Lots of components poke out the top, so you're seeing the bottoms of tube sockets, the bottoms of inductors. This particular white piece of perf board here came with the radio. Not sure what exactly it is. The previous owner did that. He seems to have gotten rid of some of the capacitors here, put in newer modern capacitors. But anyway, let's talk about what I did to it, which I think is relatively minor. The first is getting that 12 volts. So back here is where the wires come in from the power transformer. So a couple of those wires are the 12 volt, and there's also a ground. So 12.6 volt AC and a ground. You probably can't see it in there at all because it's underneath this capacitor. But underneath here, I ran a 1N4007 diode from the 12 volt AC winding over to a spare terminal on a terminal strip. And then I stuck my 1000 microfarad capacitor in. From that, you'll see there's a yellow wire that comes out. Yellow wire runs down here. Goes down over here, which is a barrel jack that I installed. You know, the typical 5.5 by 2.1. I use that to power my external digital readout. And then from that barrel jack, we've got a yellow and a black wire that come up here and supply power to the little board that I designed for the Panadapter. And let me see if we can tilt this. Need something under here so you can get a better look at the angle on this board. I don't really want to have to yank it out of here to do the video. Okay, hopefully you can see well enough in there. So this little green chunk of circuit board is the one that I built up. I did not have the time to order a board in from JLC PCB, though I probably will be doing one. I'll probably design this and fab some of them, but on here you may be able to see there's not a lot to it. There is the 2N5950 transistor, then there's a bunch of resistors and little caps and stuff. The power plugs into a 2-pin header. The RF out is via this cable here. This is a RG316 with an SMA connector sticking out the back. It's kind of hot melt glued in there till I get the right kind of bulkhead fitting. Comes in, hooks up to the board. So that's its power and its output. Now its input is this single red wire that comes over and hooks to pin 5 of vacuum tube number 2, this little red wire. And then it does actually go into a pair of, I think the 27 picofarad caps in series to give you about 13 picofarads of coupling. Some people might ask, why did I not use shielded cable right here? Thought about it. As I'm debugging the circuit, shielded cable is really super hard to work with. So I stuck with just a single bare conductor. So I may also rework how I do the coupling capacitor. Right now, there's a pair of capacitors here. They're both 27 picofarad in series. That gives you 13.5 picofarads. It'd really probably be better to take that coupling capacitor and move it from the board over here to right on the tube so that we do our coupling right there. And then, like I said, maybe come off with a shielded wire. Maybe this is fine, I don't know. They have other unshielded wires running around in here occasionally, so maybe it's fine. But couple here rather than there. And then redesign this board from and have it fabbed. And then we'll have something a little bit nicer and a little less crude than what's thrown together in here. So I'll probably follow up with a video when I do get that board built. But anyway, that's basically it. So like I said, not a whole lot to it. Now let's go try it out. Okay, let's go ahead and try out this Panadapter. So I have everything set up right now. You are seeing SDR console software running on my PC. And over here is my Drake ham radio. The Drake is currently tuned into about 7283.5. Now this is the frequency of the noontime net. And there are some guys talking. I think it's mid-afternoon, so the net may have finished up. These may be just guys chatting, or it may be the end of the net. You know, we can hear some ham radio discussion going on the net. And then, so what you're hearing is the speaker from the ham radio. This is all ham radio pipeline this is going through, but it's going out that Panadapter. It's going out that Panadapter to the computer. So looking here in the middle, you can see all of that bandwidth from that 7.283.5 megahertz. As the guys are talking, you're seeing about 2.4 kilohertz of bandwidth. See, there's another conversation over here, somewhere further down band. There's conversations here, there. We can see everything that's going on the band using this RTL, or using this software-defined radio. Tune those guys down. So a few things to know about this. So our frequency is 5645, and that is, as we said earlier, that's the intermediate frequency of the radio. We're always going to stay at 5645 in the middle. Regardless of how we tune the radio, we'll always be looking at the middle. But the actual frequency that's getting converted is going to change. So when we move the dial on the radio, we'll be able to move these things back and forth. The other thing to notice is this frequency display is inverted. So lower frequencies are over here. This is 7283 in the middle. This could be like a 7.200 somewhere around here. And higher frequencies are over here. So, you know, like 7.3, 7.4. That way. This is kind of backwards, And the reason it's backwards, I think, has to do with the mixing that goes on inside of the Drake. So perhaps it mixes it, you know, inverts it in the first mixer, and then maybe it inverts it again in the second mixer, and then you get a non-inverted signal. But just know that those frequencies work backwards, so as I go down band, we will see this one move in. So it looks like these guys have finished their discussion. There's a little tone from something. Maybe that was a carrier. Not hearing anyone talk. But these guys have finished their discussion. Let's go over here and pull whatever signal that is. Now to do that, I'm going to go over here to the Drake, and I'm going to turn the dial on the Drake. So here we are, we're at about 7240 now.
He's also looking for an extra lightning arrestor as well to probably incorporate in that installation.
So that's pretty much working as expected. I've tuned the guys back down so you can hear again. Now another thing we can do is you can actually listen via the computer. So up until now you've been listening via the ham radio, but I can turn this on. I'll unmute the computer.
$100 bill takes it. He also has a World War II military.
And now we're listening to what the SDR radio is receiving. So it intercepted that intermediate frequency, still at 5645, but you know it can tune that. And it can turn that into audio, so you can listen via your computer, you can record via your computer, and you can listen via your ham radio. Let me turn this back off. Now another thing to make note of is the pre-selector. So our ham radio has a pre-selector. It's the little dial here. It kind of tunes the RF coils and such to where we're at on the band control. And if we move that pre-selector, it should have a large effect. So there, you can see I'm kind of moving a big bubble around. It kind of lifts all signals. If we get the pre-selector way out, then all of our signal is gone. But, you know, you can see here, there's me getting the pre-selector in. That should be about peaked right there. There was one other thing I wanted to point out. Because I told you these frequencies are inverted and lower frequencies are up here and higher frequencies are down there, you might see I am operating the software-defined radio in upper sideband mode, even though this is a lower sideband band. Because things are inverted, the lower sideband is appearing on the upper side. So finally, why would you do this? Why would you take a perfectly good tube radio and hook it up to your computer? Well, the goal is not to listen on the computer. The goal is really to get this visualization. You know, you can look at almost the whole band here at once, and you can see, you know, oh, there's somebody transmitting over here. Maybe I want to go look at that. Or something just came on right there. You know, I can see a little burst of something. And there's somebody talking there. Regular pulses there. I'm curious to see what those are. I think as a visualization tool, it's really handy to have this. Even though you've got an old ham radio, and it was really pretty easy to add. Thank you for watching my video. Please visit my website at www.smbaker.com for more electronics projects and sandrail stuff. Bye.